Okay, I guess we can start. Mm, so, okay, so what we were doing yesterday uh, involved like the quadrature method, which is how to approximate integrals, right? So basically, the idea, the way we were doing it yesterday with quadrature is that like you had like an interval A, B, right? So you wanted to find. And in order to approximate it, the value for this integral, what you can do is choose some nodes. So you choose some nodes, x0, x1, up to xn, right? And you find the degree n polynomial through Lagrange interpolation that passes through these nodes. So you find the polynomial of degree n, polynomial of degree n, that at those nodes has the same value as the function, right? That satisfies that Pn of xi equals f of xi. Okay, and then the idea was to use that as an approximation for the value of the integral. So the idea is to approximate, so you approximate by the value of this integral. And the point, well, so like the two methods that we were talking about yesterday were like the trapezoid rule and Simpson's rule, right? So in trapezoid, it's just like very easy. You have like the interval a comma b, and then there are only 2 points, right? Like x0 is a and x1 is b. And in Simpson's rule, the choice of nodes was 3 points, right? So you had x0 being a, x1 being the midpoint, and x2 being b, right? And well, I mean, you can check the notes from yesterday, like because these are pretty small. These are pretty small degrees, so, like so like it was linear for trapezoid rule, and for the Simpsons rule, the polynomial was quadratic. So they're very straightforward to integrate. So you can find the rule for the approximation, and like you could imagine, like you could keep going. So if you have an interval a b, instead of like using 3 points or three nodes, you use 4 points or 5 points, 6 nodes, and you could do them like if you wanted equally spaced and all of that. So like conceptually, there's not much of a difference between understanding trapezoid and Simpsons versus like understanding what you would do with 100 nodes. Like it's kind of like the same idea throughout. And there was like this error term that we found as well. If you remember, that involved the n+1 derivative of the function. So that's kind of maybe useful to remind you of. So the error was like less or equal to the max of the n+1 derivative of x on the interval a comma b, right? I think it was n+1 factorial times, like times the value of some integral. So this is all, again, and we estimated some errors, at least for like this simple exponential square function, e to the x squared, and all those things. But kind of like now that we talked about that, it's kind of like useful to see another type of quadrature, another approximation scheme for the integral, which is called Gaussian quadrature, because it kind of like blends nicely with the stuff that we were talking about earlier about orthogonal polynomials. So it's like a very nice application of like the theory of like orthogonal polynomials that we were talking about like I guess last week. So today what I'll tell you about is sometimes called Gauss Legendre quadratures. Like you'll see why in a moment. So okay. Um, So again, that is kind of like the same idea. We will use it's kind of like a method for approximating the value of the integral. But in this case, we will use somehow the Legendre polynomials. Okay, so they first, just for convention's sake, when we were talking about the Legendre polynomials, we use the interval from -1 to 1. So I'll kind of like revert to that notation or like to that setup. So I'll assume that the interval is from -1 to 1. Okay, so this will be to approximate. Again, this is not like a massive restriction because you can always make a change of variables. If you have like an interval from A to B, you can kind of like translate and then shrink, and then you can always make a change of variables to kind of like um, put the integral on this interval. So like it's not like I think there was like a problem in the PDF if someone you could have worked out for that. So it's not like it's not like a super like it's not like a big thing. So you can always do a change of variables to turn A to B of f of x dx into an integral on the interval -1, 1. Okay. So the idea in the Gauss-Legendre quadratures is that you're going to use, again, like I know this it's kind of like the same as before in the sense that we still want to use we are still going to use a polynomial, okay? And the polynomial requires you specifying like these nodes, right? So in this case, in the case of Gauss-Legendre, you choose the nodes to be the zeros of the Legendre polynomials. Okay, so let me say that first, and then I'll kind of like show you some examples. Okay, in Gauss-Legendre, you choose the nodes, the zeros of the Legendre polynomial. Okay, so what I mean by that, just to kind of remind you, like the first few Legendre polynomials we talked about. Um, so if you remember here, like the Legendre polynomials we had discussed. Okay, so P0 of x was just like constant equal to 1. P1 of x is x. P2 of x is 3x squared minus 1 over 2. P3 of x, well, like you can write it as 5x cubed minus 3x over 2. Okay, and let me put one more. P4 of x would be 35x x to the 4 minus 30 x squared plus 3 over 2. Sorry, plus 3 over 8. So if you remember, like the way I discussed the Legendre polynomials, again, like the key property, like the most important property of these polynomials is that each of them is orthogonal to the previous ones. So for example, P2 is orthogonal to P1 and P0, and then P3 is orthogonal to P2, P1, and P0, and then and then P4 is orthogonal to P3, to P2, to P1, and to P0. Okay, so like the orthogonality is really the key property, and after that, there's kind of like some freedom in how you choose them. So I was choosing them so that at x equals 1, they have value 1, which you can see that in this case that does occur. So kind of like what you have to remember from them of what I had like mentioned before is that Pn of x is a degree n polynomial. And that Pn of 1 is 1. That's kind of like a convention. That's not as important. So this is more like a convention. But the key fact is that Pn and Pm are orthogonal, right? If n is different from m. So it's like that orthogonality requirement. Okay. So those were like, those were the Legendre polynomials. Okay. And then you could ask for each of these polynomials, what are their zeros? Meaning when do they become zero, or like you also call that like the root of the polynomial. Okay. So here let's try to put them side by side. So, like the first one, okay, has no zeros, right? Because like the constant function equal to 1 is never going to be 0. So, okay, this one has no zeros, right? How about the next polynomial? When is x equal to 0? Well, x equals 0 at x equals 0, right? So there's only one 0, okay? How about this one? When is 3x squared minus 1? Let's just work it out quickly and then when is 3x squared minus 1 over 2 equal to 0? I mean, you can kind of get rid of the 2 and then you get like 3x squared equals 1, right? And then you solve for x. And so you would find here that the zeros are x equals minus root of 1 over 3 and x equals root of 1 over 3, right? Those are like the zeros of, let me see if I can put like an arrow for each of them. So this one goes here, this one goes here, this one goes here. Okay, so those are the zeros of the degree 2 Legendre polynomial. How about let's do like I'll do the next one and then I'll just put the answer for the last one. Okay, so again, what would you do for the next one? Like, if you wanted to set it equal to 0, you can factor an x, right? And so you get x times 5, x squared minus 3 over 2 has to be equal to 0. And that is kind of like, from there, it's kind of like easy to see, right? Because the 2 doesn't matter. And so x has to be 0 or 5x squared minus 3 has to be 0. And from there, you'll get that the answer should be, let's put it somewhere in here. Let's use, uh, so from here, you'll get that x has to be minus root of 3 over 5, or it has to be 0, or it has to be root of 3 over 5. Is that making sense? Kind of like, and of course, like you can continue, like, you can continue doing this for like every single degree. I mean, in general, like you have to approximate the zeros. It's not that they're like exact closed formulas for all of them. Um, like and these ones, because they're low degree, you can kind of like find it explicitly. Even this one you can find explicitly because you can make a change of variables t equals x squared, like so you could like also solve that if you want it. In fact, like I'll just put the answer, like it's again, like we won't go that high in our examples. But if you wanted to find the zeros, like they are like plus, like that one is a little bit messier actually. Plus or minus 3/7 minus 2/7 times root of 6/5, and it also could be plus or minus 3/7 plus 2/7. Oh, one is with minus and the other is with plus. Okay. Uh, Wait, do I have this correct? Like, actually, let me just check to make sure I'm not writing something silly. Um, yes, like one is with the plus and the other is with the minus. Well, okay. Again, like I'm just showing you that, like, in low degree, you can find like explicit formulas in general, you can approximate them. What's important about them, what is it that I want to notice for you to notice about these zeros? Okay. And this is kind of like it's true for like any degree. So in general, let's see this. Like this is like an important thing to notice first. Uh, this had degree zero. This was a degree zero polynomial. It had no zeros. So it had zero zeros, which sounds a little bit weird to say it like that. Um, uh, this was degree one. It had 1 0 or one root, maybe. Let's call them roots. Uh, this one had degree two and it had two roots. Okay. This one had degree three and it had three roots. Okay. This one had degree four and it had four roots. So in general, the degree n Legendre polynomial will have n distinct roots. So in general, Pn of x will have n distinct roots. That is that the equation Pn of x equals 0 has n distinct solutions, has n solutions, which I'll call them just to kind of be consistent with our notation. I'll call them x0, x1, x2, up to xn minus 1. Okay, so that's kind of like nice. Degree n has n roots. Okay. So that's the first thing. And the other thing, like, which is not, it is not as obvious, but like it can be shown because it's actually one of the properties of like orthogonal polynomials and other stuff like that, is that all the roots are between the interval from -1 to 1. So all these zeros or all the roots or the zeros are on the interval. Moreover, all the roots are contained in the interval -1, 1. Okay, let me stop here for a second. I'll show you actually some animations with the roots so that you see how they're distributed on the interval. But is that okay? So far, so good? Is that making sense? Questions up to this point? So let me show you actually how they look like. I asked ChatGPT to do it because it was super convenient. So for example, this is the Legendre polynomial of degree 5. This is the Legendre polynomial of degree 5, and it has 5 roots. It has 5 zeros. So you can see here like the 5 roots, which are like in red. Like actually, let me see if I can zoom in, maybe to make it easier. Like hopefully that is easier for you to see. So those are the 5 zeros of the degree 5 Legendre polynomial. And then, for example, you can ask. I asked them then to do it for degree 10. So you can see there like the 10 roots of the degree 10 Legendre polynomial. Okay. And just to show you another one, I asked it to do degree 30. So because then you can see a little bit more of like a pattern of what's going on. So what happens as you increase the degree? Okay, first, like something that maybe you notice just from these ones, like is that the roots are kind of like symmetric. So they are actually, if there's like a root which is positive minus that, like that value is also a root. So they're kind of like equally like symmetric about the origin, which you kind of may see here, right? So again, that's not like an obvious property from the definition of the Legendre polynomial, but it just happens to work that way. So it's kind of like nice that the roots are symmetric. But it, even more important than that, I guess that's not as important as the fact that if you notice that roots are not equally spaced, right? Like so the roots are not at the same distance from one another on the interval, right? So like they actually tend to accumulate towards the edges the of the interval, like so towards -1 and 1, there are more roots accumulating. And that is actually similar to what happened if you remember when we talked about the Chebyshev nodes and the Chebyshev points, they actually had like a similar behavior to that. And again, for reasons like which are a bit more technical, when you're doing polynomial interpolation, this is kind of like a useful property to have for this thing related to the Roentgen phenomenon that I kind of like briefly had told you a little bit about. So it's kind of like actually like a nice feature that the roots are not equally spaced, and they actually tend to accumulate towards the edges of the interval. So that's kind of like what I wanted you to actually see from the distribution of the roots here, that will tend to happen. And in fact, they kind of like accumulate towards the endpoints in a similar way as the way in which the Chebyshev nodes like accumulate towards the endpoints. So that's also like a nice like feature that they have. So let me write down those two other things because like they're actually, again, for like more advanced reasons, they are like some nice properties to have for like approximations of with polynomials. So let me see if I can write that down. So also so useful, also useful that the roots of the Legendre polynomial are distributed in a symmetric way with respect to the origin. So one way to say that is that if R is a zero, then minus R is a zero. So if R Pn of R equals zero, then Pn of negative R is a zero. So they come in pairs. That's what I'm trying to say. So the roots come in pairs. Okay, and the other thing that's kind of like nice about them, which is also what I was showing you in the animation, is that they are like they accumulate towards -1 and 1. So they're not uniformly spaced, right? So also the roots of Pn of x are not uniformly spaced, meaning that um, in fact, maybe let me put it like that. In fact, they're more as you approach the endpoints, -1 and 1, there are more roots. In fact, the roots accumulate near the endpoints and -1 and 1. Okay. Um, so the idea in the Gauss quadrature is basically to do exactly the same thing that we were doing yesterday, but choosing the polynomial like with using these nodes. Okay, so that's let me explain what that means, and then I'll kind of like maybe do an example first, before I tell you more like properties and why this is a useful thing to have. So how okay, I'll call this the n+1 Gauss quadrature approximation. So here's like the n+1 Gauss Legendre quadrature method. Okay, so the idea is that you choose an integer n. Okay, so here's like the algorithm. You choose an integer n. Then you look at the Legendre polynomial with n+1 of degree n+1. So like find the find the zeros of p n+1 of x. Okay. The reason for using that one is that the degree n+1, the Legendre polynomial has n+1 zeros, right? So um, so they are called x0, x1, x2 up to xn, or call them like you know. Okay, and with those n+1 points, right? You can do exactly the same thing that we were doing yesterday. You can find a polynomial of degree n+1 that passes through these points together with f of xi. So if you're given a function, if you're given a function f of x, f of x, uh, find the use Lagrange interpolation to find the polynomial of degree n that passes through x0, f of x0, x1, f of x1, up to xn, f of xn. Okay. And so the idea in Gauss Legendre is to approximate the integral from -1 to 1 of that function by the integral of this polynomial. So in Gauss Legendre, you approximate the integral from -1 to 1 of f of x dx with the integral from -1 to 1 of p n of x dx. Is that okay? So far, so good. Is that the idea making sense? What I want you to notice is that this won't agree with the previous approximations because now in Simpson and trapezoid, like the points were equally spaced, right? And here x0 up to xn are not equally spaced. So this will not be the same approximation number as like what we were doing before. So, so notice this won't yield as trapezoid or Simpson. Since the nodes were equally spaced. Okay. So is that making sense? So far, so good. Now, in fact, in this case, and this is how usually would if you open the textbook, I mean, or like any sort, any reference, you you will find this written down in a slightly more explicit way because you can give a more explicit way for a formula for the polynomial, right? So remember that using Lagrange, recall that you can kind of like give a formula for the Lagrange polynomial, right? Because of the interpolation formula, was it? So this would be up to n of f of xi. And I think this is how I was calling them in class, right? Where L of n I x, what was that? It was the product. Okay, it was like so over the j distinct of I of x minus xj divided by the product of j different than I of xi minus xj, right? That was, I mean, I'm just saying, like, in fact, that's how you would find the Lagrange polynomial, right? You would compute these things, and then you multiply by f of xi, right? And that gives you, and that would have given you the polynomial. So, in fact, when if you had to integrate the polynomial, right? So if you integrate this polynomial from -1 to 1, what does that tell you? It tells you that the integral of Pn, the integral from -1 to 1 of Pn of x dx. How do you integrate this? You integrate like the integral of a sum is the sum of the integrals. So it's just really the sum of I equals 0 to n of the integral from -1 to 1 of f of xi times ln of I x dx, right? But f of xi, that is just a number, right? Like that's a constant. Like that's just the value of the function at that particular zero of the Legendre polynomial. So you can take that out of the integral. So you end up getting the sum from I equals 0 to n of f of xi times the integral from -1 to 1 of the ln of I of x dx. Okay? And the thing here is that what's useful to understand is that this has nothing to do with the function, right? Like that just has to do with the zeros of the Legendre polynomial. So this is the same regardless of f, right? That has nothing, this has nothing to do with f. So this is independent of f. So like literally, well, like, there are tables or like, I mean, now these days it wouldn't be on tables, right? But like, you can kind of compute these quantities ahead of time and kind of like have them ready to go. Like, so because these are always the same numbers, right? Like they don't change from one problem to the next. The only thing that depends on the problem is a function that you were given. So these like are sometimes called weights, but they're just or coefficients, like but they're just like numbers. So like I'll call them they can be computed like ahead of time. That's what I'm trying to say before the problem is like kind of like ready to go. So they can be computed. Okay. And so if you and so like you can just in the from that perspective you can write like the integral of the polynomial in a kind of like nicer way as kind of like the sum from 0 to n of the values of the function at xi times these numbers, which I'll just call them wi for weights. So it like that kind of like gives you like a kind of like a very concrete formula because again the weights everyone, well, not everyone, but you can just look them online or on the textbook or anywhere. Like it's not something that you have like it's something that the computer would have like available, like to just like extract. So it's not like something computationally that it's already has been computed and it's kind of like ready to go. So in fact, when you have like a numerical method, like the thing that consumes the most time is evaluating the function at these nodes, because that's kind of like the new part that you have to find. This is kind of like that's dependent on the function, whereas these weights are none. So like actually most of the computational cost of evaluating the integrals is just evaluating the function at the nodes. And so that's kind of like interesting. So in fact, most of the computational cost evaluating the integrals is spent in just computing f of xi. Okay, so like maybe before I do the example, let me show you what I mean by the weights. So again, like I mean, it's on the book also, but like if you go to, for example, if you just go to like Wikipedia, you enter Gauss Legendre quadratures, and it gives you like basically this formula that I was just writing um 2 seconds ago, right? I mean, they just have like a different convention because I'm starting them like the sum at 0, but that doesn't matter too much. It's kind of like the same structure, and then and so here the points refer to the roots of the polynomial, and then the weight just refers to what's the corresponding value for the integral, like associated to the root when you do the like the Lagrange interpolation. So all that I'm trying to say is that like these things are kind of like well known, like so you don't have, and I wouldn't ask you to compute them. I will just give them to you because like I mean you can look them up. That's what I'm trying to say. So there's not like um not like a big thing, like it's more like understanding the principle, and that like numerically really where the effort goes is in evaluating the function at the points, which is kind of like a fun thing to notice. Um, so let me give you an example. And then after that, I'll tell you why this Gauss Legendre is kind of like a cool method. So let's do actually a similar problem to the one we were doing yesterday. So let's use Gauss Legendre to approximate um, this integral. So it's not the same that we had yesterday because yesterday was from 0 to 1, but they are almost the same, right? Because the integrand is even. So this would actually help us to approximate the integral from 0 to 1 from using n equals 1, n equals 2. Okay. Okay, so n equals 2, what does that mean? It means that you look at n plus 1. So you look at the degree 3 Legendre polynomial. So here you use P3 of x. Okay, P3 of x was like, x times 5x squared minus 3 over 2, and then the zeros, like, the zeros, we already discussed them, like the zeros on the interval -1 to 1, the zeros are x equals 0. The other one would have been like, root of 3 over 5, which is roughly 0.77. I'll just leave it like that. And the other one is symmetric. So they're symmetric. So once you know one, like, just reflect it. So it would have been minus root of 3 over 5. So minus 0.77. Okay. So just to kind of like stick to the notation we have been using throughout the course, this is kind of like my, x0, this is my x1, and this is my x2, right? And so like the points are, you know, minus 0.77, f of minus 0.77, and then 0 comma f of 0, right? And then 0.77, f of 0.77, right? So you're trying to find that degree 2 polynomial through, you're trying to find a degree 2 Lagrange polynomial through these 3 points, right? And so again, like the formula, I'm going to write it in more explicit terms than what you need, but so that you see it. So the formula is for P2 of x is, so P2 of x would be f of minus 0.77. Let's call this one, I'll call it just like L0 to make my life easy, plus f of 0 times L1 of x plus f of 0.77 times L2 of x. Okay, and again, like, not that you need to write it down in so details, but just to kind of connect it to what we were doing before. So what would be L0 of x? That would be what? Like, it was like x minus x1 times, x minus x2 divided by x0 minus x1, x0 minus x2. I'm just writing it down so that you see that if you wanted, you can literally write down in a very explicit way what all of this is. So, so the other one was x minus x0 times x minus x2 times x1 minus x0 times x1 minus x2. And then the last one would be x minus x0 times x minus x1. And then x2 minus x0, x2 minus x1. Okay, so I'm just putting it out there so that you notice explicitly that this has nothing to do with f, right? That only has to do with the zeros of the Legendre polynomial, right? Like because x0, x1, x2 are the zeros of the Legendre polynomial. So this is unrelated to f, okay? So nothing to do with f, independent of f. Nothing to do with f. And you have the values for x1, x0, x2. So like that's what you would do. Like that. That's what I'm saying. Like people can just like find the values for these integrals ahead of time. So they are found and they are known. Um, for many decades now, probably. So what that means is that the approximation is then approximated with again like what numbers should I do? Okay. F of x0 times the integral from -1 to 1 of L0 of x dx plus f of x1 times the integral from -1 to 1 of L1 of x dx plus f of x2 times the integral from -1 to x of L2 of x dx. And these are the weights, like, this is what I was calling before the weight 0, the weight 1, and the weight 2. Okay. So you end up getting, you know, if you plug in, if you go to the table, like which is in the book or like a Wikipedia or whatever, you would get, okay, so you end up finding f of minus 0.77. The weight 0, again, like you can find it, for example, in Wikipedia. It's like 0.5555 plus f of 0 times 0.8888 plus f of 0.77 times like the weights are they are symmetrical, so like because of like how the distribution of the zeros are located and all that stuff. So the weights also come in pairs, which is nice. And so you just like if you just substitute all of these, I mean, of course we're approximating already, but if you substitute all of these, you get e to the negative right 0.77 squared times 0.5555 f of 0, okay, it's e to the 0, which is going to be e to the 0 times 0.8888 plus e to the 0.77 squared 5555. Okay, and if you know if you do that, all of that, you roughly will get 2.90. Like and now this is just a question about plugging in. So this will give you 2.90. Okay, so what that means is that the integral from -1 to 1 of e to the x squared dx is roughly 2.90. And for example, just for comparison's sake with yesterday, because yesterday we were doing it from 0 to 1, right? So what is so the integral from 0 to 1 of x squared dx, which is just because like the integrand is even, it's just 1/2 of this one, right? So this is one is roughly, according to this method, it would be roughly 1.45. Okay. And like yesterday with Simpson's rule, if you remember, like compared with yesterday, where with Simpson we found 1.48, and like the real value, like by real I just mean like the one like Wolfram alpha would give you, you know. And then the real value was 1.46. Okay. So it's a little bit closer to the real value, but like I mean, it's well, like it's like very in this case, like it's a very similar value, to the one you would get with Simpson's rule. Um, well, I still haven't explained what's kind of like cool about the Gauss Legendre method, which is what I'm going to do next. But at least I wanted to give you like an example to just show you that it is the same philosophy approach that we were using yesterday. You choose the nodes, you find the polynomial, you integrate the polynomial. So none of that changes. The only thing that changes is what the nodes are. So yesterday the nodes were equally spaced. Today the nodes are the zeros of Legendre polynomial. Is that making sense? Are there any questions about this so far? So good. Okay, so let's take a 5-minute break, and when we come back, I'll tell you why this method is kind of like interesting because it kind of like performs better than others, and I'll kind of like say in what sense it performs better in a kind of like very surprising way. And it's kind of like a nice application of orthogonality, so that's why I wanted to do it, so that it connects with some of the stuff that we were doing like before the for the second exam. So let's say 11:30. So at 11:30 I'll tell you uh, why this method is kind of like interesting. Okay. So just double checking. Everyone can hear me because like yesterday when I put the AirPods first time, like it wasn't working. Is that okay? Okay, perfect. So as I was saying, like so far, it's not super clear what's the advantage of using the Legendre Gauss approximation. But now what I'm going to explain to you is why that's useful. By the way, so Um, as I think I can mention this before the exam, but like the only quiz that we will have left is on Monday. So I'll kind of like send you the quiz problems today, based on what we have done yesterday and today. After today, what we will do tomorrow is talk about differential equations, and on Monday we will talk about differential equations as well. So like I'm leaving the last two classes to discuss like approximations of ODEs. Um, but it will, like it will be kind of like similar to some of like the stuff we did before. So it's going to be like a nice connection to some of like the earlier material that we discussed in the course. But that's kind of like the plan for, in terms of like topics for like the remaining two classes. And then on Tuesday, as I got told you, there's no lecture. I'll just I'll start the meeting, like the regular meeting for like office hours, like, answer questions. And then we would have like the exam on Wednesday. So that's kind of like the idea. Okay, so let me explain a little bit about why Gauss Legendre is interesting approximation. Okay, so let's just talk about that. Okay, so just as before, right? Just like yesterday, um, we had kind of like mentioned this before, but like if yesterday, like for example, in the trapezoid rule, if you were using the trapezoid rule for a linear polynomial, there's no approximation. The answer is exact, and in the in Simpson's rule, because the answer would have been exact for a quadratic polynomial. So here, like just like as yesterday, the n+1 Gauss Legendre is exact for a polynomial of degree n. So like similar to yesterday. Oh, well, I mean for a given n, Gauss Legendre is exact if f of x happens to be a polynomial of degree n. Okay. Okay. And that is just because, like, just like yesterday, like maybe I can go to yesterday's notes to tell you why that happens. It's not that different from why we were doing like last time, because if you remember the error estimate, um, where do I have the error estimate? So, whenever you have like a polynomial, the error estimate had to do with the n+1 derivative, right? So if the function happens to be a polynomial of degree n, its n+1 derivative would be zero. So like there's no error in the approximation. Like, so that's kind of like the rough idea. Like that kind of like works just like as like yesterday's class. Why like the formula is exact for degree n. What's kind of like new, and this is like actually very unique to Gauss Legendre. What's um what's like a special feature of Gauss Legendre is that it continues to be an exact formula if the polynomial has degree up to 2n+1. What's like, and this is like the a special feature is that the Gauss Legendre approximation to be exact, well, with integer n, continues to be exact even if f of x is a polynomial of degree 2n+1. Okay. So just before explaining why this is true, like just to make it more concrete, like so if for example n had been 2, right? So like what I'm trying to say is that if x if n is 2, right? If n is 2, that is actually what we were doing in the earlier example, because in the earlier example I chose n equals 2. So again, you would use like the roots of P3, okay, which were these three roots, okay. Like we were like approximating with the sum from I equals 0 to 2 of f of xi times these weights, right? Um, And so what I'm saying is that, like, what you would expect, what like kind of like what you would expect is that this formula is exact for polynomials up to degree 2. So you would expect, so this would be exact. This is exact for when f is a quadratic polynomial. But because it's Gauss Legendre, more is true, so it's exact up to degree 5. But 2n plus 1 is in this case 2 times 2 plus 1, which is 5. So in fact, the formula, this approximation continues to be exact for degree 5, up to degree 5. So this approximation. Okay, so kind of like what I'm trying to say is that Gauss Legendre outperforms like like based on what your expectations would have been, like it performs better than your expectations, like So it is like a more like accurate method for higher degrees. Um, okay. And so what I'm going to tell you now is why is this true? Why does it work better? So why does this happen? I mean, it's kind of like a bit of an abstract proof, but it's kind of like worth looking at it because it does like a nice excuse to go through some of the material we have done before. So first, I have to just give you like a quick reminder of how division works. So just like you know, a refresher on long division. I promise we won't use it too much, but Okay, so like here's like a very simple example with numbers. Like that 2 divides 6, right? Since basically 6 is 2 times or 3 times 2, right? Let me write it that way. So like you would say that 2 divides 6 because 2 appears as a factor of 6, right? So 2 appears as a factor of 6, right? That's kind of like natural. Now there are things that there's something similar you can do with polynomials, which you may or may not have seen that before, but you can kind of like talk in a similar way about polynomials. So for example, you could say that x squared plus 1 divides what, x cubed plus x. Why would you say that that divides it? Because it's kind of like not too bad to do it here, since x cubed plus x is x times x squared plus 1, right? You can factor out an x, and then x squared plus 1 appears as a factor, right? So x squared plus 1 is a factor of x cubed plus x. And that's kind of like the whole point of factorization, right? When you learned about factorization of polynomials, it is like a form of like, finding like it's like the polynomials that divide it, like the factors are the polynomials that divide the bigger polynomial. Okay. Now, So, okay, that's kind of like an analogy, right, between numbers and polynomials, but there's kind of like a stronger analogy because here's another case, right? So 2 doesn't divide 7 in the sense that, 7 over 2 is not like an integer. That's what I mean by that. But like this is not some like maybe something that you may have seen like when you were kids, like, or it could be one of these topics that has been removed. But in this case, there's a thing called like long division or like the Euclidean algorithm that tells you that you can write 7 as, kind of like 3 times 2 plus 1, right? So here 1 is called the remainder, okay? And then here 3 is kind of like the quotient. It's kind of like the integer part of the division, right? Because if you did 7 over 2, that would give you 3.5. So you keep like the integer part, so it just gives you 3, okay? So this is kind of like sometimes called like long division or like the Euclidean algorithm. Um, and kind of like the only reason why I'm bringing this up is because you can do something exactly similar with polynomials, okay? So for example, so something like analogous to this works with polynomials. So something like this also works with polynomials. Similar works with polynomials. Where like for example, you know, uh, like x squared plus 1 does not, it doesn't like it won't divide. Like, so this polynomial doesn't divide that polynomial, this cubic one that I'm writing, just basically because that cubic polynomial doesn't have x squared plus 1 as a factor. That's something you can check. You can check it explicitly, so it doesn't have it as a factor. But kind of like the next best thing is to kind of like do like a long division. Okay. And if you did long division, not that you need to know how it, like, how to do it. Like, I'm not going to ask you how to do it. It's just telling you that it works because I will need this in a moment. Okay. So if you do long division, it kind of like allows you to write the bigger polynomial, the polynomial of higher degree. And it kind of like in a similar form as the other one. So you can write it as x minus 1 times x squared plus 1 plus x plus 6. So this is kind of like the remainder. And this one is kind of like the divisor. I mean, this one would be kind of like the quotient. Okay. So my point is that with polynomials, there's something similar that happens where like you can kind of like in the same way in which you can kind of like perform long division on numbers, you can perform like long divisions on polynomials, and that's kind of like a fun part to learn how to do. But like it may have been de-emphasized like from like high school curriculum these days because it's a little bit more tricky to do. But it's kind of like a very useful idea. Okay, and I promise I'm about to use this in a moment. As you'll see in a second. Okay, so I just was mentioning this so that you know that if you need it, you can do long division on polynomials. Okay. So back to what I was saying, to my claim. So what I was saying is that if you have a polynomial of degree n 2n plus 1, okay, so here f of x is going to be a polynomial of degree 2n plus 1. Okay, so my claim is that the formula that you get from the Gauss quadrature is exact. Gauss Legendre quadrature is exact in this case. Okay, and we had Tn of x. Let's see. Let me write it. Let me see how I'm writing it. Uh, okay. So this is the degree n polynomial that passes through x0, f of x0, x1, f of x1, up to xn, f of xn, right? And here x0, x1 up to xn were the zeros of the degree n plus 1 Legendre polynomial. So here, uh, x0, x1 up to xn are the roots of the Legendre polynomial Pn plus 1 of x. Okay, so my claim is that the integral, if you were to integrate this polynomial f from -1 to 1, that gives you the same value as the integral of the approximating polynomial. So the idea, my claim, is that the integral from -1 to 1 of f of x dx is the same that what you would get from the integral from -1 to 1 of Pn of x dx. Okay, which if you think about it for a second, that seems weird because again, this is a degree 2n plus 1 polynomial, and this is a degree n polynomial, and I'm kind of asserting that when you integrate them, they will give you the same answer. Okay, so like it's just like worth thinking about it for a second because again, like this one has degree n, and this one has degree 2n plus 1. Okay, so it's kind of like miraculous that they would have the same integral. That's kind of like the useful thing to notice. Like, and like, it's not obvious at all. That's what I'm going to try to explain to you. So why does that happen? Oh, so let me just use like write this in a way that this is like make it clear that this is like a lowercase p, not uppercase. Okay, so why does that happen? Okay, why is this true? And this is where you use long division. So because of long division, you can apply long division to f of x and the Legendre polynomial. So basically what you can do is you apply long division to f of x and the Legendre polynomial Pm plus 1 of x. Oh, actually, let me see if I can keep the same colors. Okay, so just based on the structure that I was giving you um, before, this would give you, you know, let me see if I can zoom out so that you can compare it. So when you have the polynomial, you have the factor, you have the polynomial you're trying to divide by. So you're trying to divide by the degree n plus 1, the Legendre polynomial. So that gives you a quotient. I'll call the quotient Q. Okay, this is the quotient. It has to, in principle, it would have degree it would have degree n because this is a degree 2n plus 1 polynomial. So I'm going to put it downstairs like as subscripts, like the degrees. So this polynomial has degree n plus 1. This one has to have degree n so that when you multiply them, you get 2n plus 1. So it matches like the top degree of the polynomial. And then there's a remainder. And kind of like the way the division algorithm works is that the remainder, like it has at least a degree less than the polynomial you're dividing by. So the degree of the remainder cannot be bigger than uh, n plus 1. It cannot be n plus 1 or higher. So actually it has to be degree n. At most, like it could be constant, it could be degree 1, but it cannot go beyond degree n. So again, this is the remainder. And this is the quotient. Okay. So what happens? What is okay, so we're trying to compare these two integrals. So let's use this equation to integrate from -1 to 1. So if you integrate this from -1 to 1, that's the integral from -1 to 1 of Qn of x times Pn plus 1 of x dx plus the integral from -1 to 1 of Rn of x. Okay? So far, so good. So, I mean, that's just what you get by integrating both sides of the equation after you did long division. Now, what's interesting is what happens with the first term. So let's just focus on this term first. Okay. So let's focus on this one first. So what is the integral from -1 to 1 of Qn of x times Pn plus 1 of x dx? Well, this is where like the inner product shows in. That is the inner product between Qn and Pn plus 1, right? Is that making sense? I mean, that is actually how the inner product was defined, like, or the dot product, if you want to call it dot product. It's just multiply the functions and integrate from -1 to 1. Now, I don't know if that's super obvious, but can anyone take a guess on what this inner product should be? Anyone wants to, like, the answer should be like, if I'm asking for a number, like it should be like an obvious number, like as the answer. Let me make it more explicit. This is a degree n polynomial, right? This is a degree n polynomial, and any degree n polynomial is a linear combination of the Legendre polynomials up to degree n. So this would be a linear combination of the degree n Legendre like of the Legendre polynomials up to degree n. That's actually one of the other properties of Legendre polynomials, that any polynomial can be written as a linear combination of them. So, and these, because of the properties of the inner product, which are the same as the properties of the dot product, this is kind of like the sum from I equals 0 to n of how does that look now? Maybe that's easier now. What is this? What is this inner product then? This is a n plus 1 Legendre polynomial, and this is a Legendre polynomial of a degree less than that one. Yeah, so it's just like automatically orthogonal. That's how you define them, right? So this vanishes automatically, which is the cool thing. So this is automatically 0 because of orthogonality. Okay. And so that means actually that this integral like goes away. So actually the integral from -1 to 1 of f of 2n plus 1 of x dx ends up being the same as the integral from -1 to 1. Okay. And we're almost there. Like now it's very cool what's going to happen. We are almost there because what happens next? um, well, these this is a degree n polynomial. This is a degree n polynomial. So you know the Gauss Legendre is exact for degree n polynomials. So Gauss Legendre, because it's got degree n, so Gauss Legendre is exact. So that this is just the same as what we had before. It's just like, I mean, it's going to be like the value of the it's kind of like this formula. It's the value of the function times the weights, like because Gauss Legendre is exact. It's just that the function here it happens to be r, not f, right? Okay. So this equals, because Gauss Legendre is exact, this would be the sum from I equals 0 to n of r n of xi times the weights. And again, that's kind of like the beauty of this, that the weights have nothing to do with the function, right? Like again, like remember the weights are completely independent of the function. So it all boils down to what is Rn of xi. So what is Rn of xi? And if you go back to the equation, sorry, just to go back for a second, if you go back to this equation, again, the equation that you get from long division, oh, you can evaluate it at x equals xi. So evaluate at x equals xi. So you get that f of xi equals qn of xi times the degree n plus 1 Legendre polynomial evaluated at xi plus Rn of xi. Okay? So I have no idea what this is, right? I have no idea what this is, but I do know what this is. What is the Legendre polynomial of degree n plus 1 evaluated at xi? That is zero also, because xi is a root of that Legendre polynomial. So this is zero precisely, almost by definition, zero, since xi is a root of this Legendre polynomial. So because this is zero, zero times whatever is zero, so you end up finding that f of xi is the same as Rn of xi. Okay. So if you go back for a second to so substituting that back in, that's called asterisk that equation that we just found. What are we finding? We found that the integral from -1 to 1 of f of 2n plus 1 of x dx was the same as the sum of I equals 0 to n of r of xi times the weight. But because of what we just found, that is the same as the sum of I equals 0 to n of f of xi times the weight. And that is precisely like the Gauss Legendre approximation. That is how you would approximate the value for the integral, right? So this is the value from Gauss Legendre, right? So this is the Gauss Legendre approximation. So it tells you that, but this was all like a bunch of equalities. So there was no error here. So that kind of like proves you that that shows you that the integral happens to be exact up to degree 2n plus 1, which is a kind of like a really cool thing. What I like about it is that it's just, I mean, like it's not like that you need to know the proof, but it's just kind of like to appreciate how the theory, like the fact that the general polynomials are orthogonal, kind of like saves the day. Because if you didn't know that the general polynomials are orthogonal, so you would never have been able to replace this with zero. And if you don't know that this is zero, you cannot get rid of this integral, right? So you wouldn't have not known anything. So that's kind of like where, like, that's a kind of like a very, unexpected application of orthogonality. Uh, let's see. Uh, And okay, and once you know that, and that I'm not going to explain because it would take too much time. But once you know that, you can improve. Once you know that Gauss Legendre is exact on polynomials of higher degree, you can use that to improve the error calculation. So just like as a remark, because again, we are not going to use this. Uh, Once you know that for n, Gauss Legendre is exact for polynomials up to degree 2n plus 1, you can kind of like find an improved error formula. You can find error formula for Gauss Legendre, which I mean, I'm not going to get into the error terms for Gauss Legendre. But I just want, at least I will write it down so that, um, which would be that, that basically the error is going to be less or equal to the max of the 2nth plus 1 derivative of -1 to 1, then 2n plus 2 factorial times the integral from -1 to 1. Oops, sorry, let me see. Oops. Times the integral from -1 to 1 of x minus x0 squared up to x minus xn squared. Okay, so again, I'm not going to use this formula for the error. All that I'm trying to say is that, like, if you get all the errors until now, if you were using a degree n polynomial, the error involved the nth plus 1 derivative. But once you know the Gauss Legendre works up to degree 2n plus 1 polynomials, that allows you to do one more derivative in the error calculation. Um, um, and so, or yeah, I may, oh, 2n plus 2, I think it should be here. Sorry. Yes, I think it's 2n plus 2. Yeah, 2n plus 2. So once you know works well up to degree 2n plus 1 polynomials, it kind of like gives you, for not for free, you still have to show it, but it allows you to kind of like improve the error calculation for any function up to the so that it involves the nth plus uh, 2n plus 2 derivative of the function. Okay, which is kind of like now that is like a true like advantage to before, so it's kind of like a nice illustration about, like, orthogonal polynomials, and, like, why sometimes like not using equally spaced points can be convenient when you do the approximations, etc. And I think it's like I mean, I think that together with what we were doing yesterday gives you like a good like idea of how like some of these numerical approximations work for integrals. Of course, there are many more things that you can try, but they're kind of like very close in spirit to some of like the stuff that we were doing. So it's kind of like better to just like focus in the last two classes like on differential equations, so that you also see how that works. So that's what I'll start doing tomorrow. And yeah, I think this is a good place to end, unless anyone has any questions. Uh, I'll probably grade them like on Friday or something like that. Well, no, for the first exam I already graded it. You can find your grade on the first exam like I graded that like 2 weeks ago. Well, you have to click on show rubric. Uh, did you find it now? Okay. Let me see if I can. Okay, so go to the assignment to the uploaded one, not to go to the exam assignment where you uploaded it. Um, Let me see if I can. Yeah. So if you click on that assignment, you should. Uh, okay, good. So you can take a look at it and let me know if you have any questions. I also like you can compare with the solutions that I wrote. I tried to make some comments on the rubric to say where I was taking off points. But yeah, you can take a look at it and then just let me know if anything, you know, if you had a specific question. Yeah, no worries. Anyone else? Okay, in that case, I'll see you tomorrow. That sounds good.